Bismillahirrahmanirrahim. Welcome to Transistors and Application. And last time we are discussing in the episode 4 about the details of the inside working principle of the bipolar junction transistor. And in today's episode, also we had already discussed about the transistor's current, but in today's episode we will try to recap some concepts of the and we will continue the last time concepts of the transistor currents. And as you know, we had discussed about the amplification, as I explained in the second last episode, that we had discussed the started the discussion about the amplifier transistor, bipolar junction transistor as an amplifier. So today, in today's episode, we will try to discuss transistor current gain. Because we are using the transistor as an amplifier, so current gain is a natural process, because when we talk about the as an amplifier, definitely there is a gain when the output divided by input value of any equipment or you can say that any electrical quantity, just output when divided by input, then if the result is greater than, if this ratio is greater than 1, it means that there is a gain. If it is equal to 1, then it means that output is equal to the input. If it is greater than 1, it means there is a gain, something gain, and then this is called an amplifier process. But if it is below 1, then there is an for example 0.9 or 0.8, then this is called attenuation. Okay, so but we are discussing this case when there is a gain. So transistor gains, first of all, let's started discussing the drawing of the bipolar junction transistor. And this is a bipolar junction transistor. This is a NPN. Okay, and this is the collector, this is the base, and this is the emitter. And this collector here is grounded, and this collector is this is a common collector circuit, as discussed in this from the start of this series. We had discussed in every episode the common collector, and we will try to rebuild the concept again from the last episode. And this is a common emitter. Here the resistance is used in series with the biasing source, that is here this is the biasing source. The positive side is connected with the P, so here positive, and negative side is connected with this emitter, because this is N region and this is P region. Overall, this is the base emitter region. Remember that in order to operate the transistor as an amplifier, I already explained in the previous video that base emitter junction must be forward bias, while the second base collector junction must be in reverse bias. So these conditions must be fulfilled. I know that there are further conditions also available, that both can be forward bias, both so in active region, both can be in reverse bias to cut off region, and so on. But we are discussing right now as an amplifier, so these conditions must be fulfilled in order to operate the bipolar junction as a amplifier. So this is the biasing source here to connect it to make sure that the base emitter junction is forward bias. And this series resistance here can be renamed as a R, and because this is the series resistance at the base point, so a capital B in the subscript. Remember that in the whole labeling of the diagram, I used in the subscript capital letters. These capital subscripts represents that these terms are used for the DC, and in the upcoming episode I will also explain this in details. Anyway, here this is the VB, or you can just write VB, which means this is the voltage for the biasing of the base voltage. And here this is another resistance. These resistances are just for the limiting purpose, and they have not any other aspect here as well, just to protect our base collector junction and our to set our outside polarities within the range of the ratings of the transistors, nothing else. And this resistance here is at the point of the collector, so we can say that this is RC, renamed as RC, which shows that resistance at collector in series with the external source, that is the at collector. So in order to set the collector base junction reverse bias, this is N region. N region must be collected with positive, and here negative, positive, negative. This negative reaches here and it is connected with the common emitter that is coming from the VBB, and this negative, and here N is connected with negative, and you can see that now the positive side of the region of the base is connected with positive side of the VBB, and here N is connected from the both side negative, and so it is forward bias. This is forward bias and this is reverse bias. You can see that this, we can rename this as a VCC or just VC because it is connected at the collector terminal. And okay, if let's discuss about the other, that is the second case in which we will discuss the, this is the second case in which this is a PNP, and here the same situation. This is a series resistance named as RB because this is connected at base point. Now this is the base, this is now again emitter, but now at base this is now N region, and at emitter this is a P region, because in this condition also we have to forward bias the base emitter region, but our biasing polarities must be changed in order to operate it as an amplifier. Because we want to operate as an amplifier, so this condition must be, as you can see that everything is reversed, and this is now VCC, and here positive is coming to the P, and here positive is coming towards the P from the VBB, and both of these will again trying to forward bias the base emitter junction because negative is connecting at the N side. So this is the same, just the if we change the NPN to PNP, our current direction will also reverse. So let's talk about the current directions, and we are discussing the electronic flow, and this is the discussion, this is the direction of the current, and this is because these are the negative, so negative towards positive, this is I emitter, and here current is outing, this is IB, emitting current at also on the collector, emitting and leaving this circuit, so this is also I from negative towards positive terminal IC. So at this current direction will be reversed from negative towards positive, and so this is IC, and here current is entering to the base junction because this is the negative, here potential is connected from the outside, so this is called IB, and here the current is leaving, both current is entering from here and leaving through this side, and this is called IE. And remember that there is another important tip that I explained in the previous video, that I emitter is equals to IB plus IC. In the previous example I showed with the help of an example, let's say 20 electrons are entered from at the emitter point, 5 will be leave to this side, and most of the electrons, major part will go through the state and will be emitted from this bipolar junction transistor, 15 electron through the collector junction. And now if we discuss this, you can see that most of the electron, that's why here this is not, resistance is not used, just to show that this is at a higher concentration emitter, base and collector have a little bit lower percentage of the electrons. And another representation is this in some books, this is emitter, base and collector, then at emitter there is a positive sign. This positive sign also shows that the emitter has a little bit higher concentration of electrons. And in some books emitter they write that emitter is heavily doped, collector is moderately doped and base region is lightly doped. Second important thing to note over here is I use here the two separate batteries to power this, but you can also power up this circuit with a single. Most of the times in some books I have seen that they power this circuit with a single battery. For example, this VCC, remember that this VCC, if a VCC is much greater than VBB, so if these two batteries are not connected in also practical cases, most of the times we use single battery. And here you can see if VCC, then we can use a resistance circuit and to provide the current here. And for example, if this is a 20-volt battery and we need here, let's say 3 volt, so we can make a circuit, and by using there are many circuits are available that will provide the 3-volt connection to this side. Okay, let's talk about some other terms that let's talk about now the DC beta. And what is DC beta? DC beta is the gain of the transistor, that shows the how much gain. As I explained, that output over input, if answer is greater than 1, that shows that there is a gain, something gain. And this how much gain is obtained by the DC. And what is the output and what is input? Beta DC shows the output over input. Output is available through this collector junction. This is the collector junction, and output can be taken from this collector junction. This is the output, our output. And what is our input? That is the base IB toward this side. This is, let's say, our input. So this current, I explained, if 15 electrons here, you can see that. Let's talk about our previous example. 15 electrons divided by base is relatively small, let's say 5. 5 divided by 15, that is answer is 3. So answer should be always greater than 1. That's why I said that it is gain. So if the answer of the beta DC will never be never ever less than 1, because we are operating our transistor as an amplifier. So this is called the beta DC. In most of the cases, the values of the beta DC will be range from 20 to 200 or even greater. It is mentioned on the data sheets. One more important thing to tell over here, that is the hybrid parameter. This beta DC is a hybrid parameter. What is mean by hybrid parameter? We will discuss and cover this in another series in details, but right now hybrid parameters are those parameters that are used in the case of the amplifier characteristics, such as to calculate the voltage gain, input output resistance gain, etc. The major advantage to use the hybrid parameters are the voltage values of the, as this is the beta DC, the values of the circuit components are easily available, number one. The second procedure followed is quite simple and easy to understand, but we will discuss these in details. As you can see, the simple formula output by input, it is very simple. But let's talk about, and the beta DC is most widely used in our calculations. There is another parameter that is called alpha DC, or you can see that also known by DC alpha DC, same thing, alpha DC. And alpha DC is the ratio of collector divided by emitter. IC, that is here, this is IC, and divided by IE. So IC is always less than IE. As we again discuss our previous example, 15 divided by IE, that is here in our case that is 20. So 15 divided by 20 always, as I explained, emitter is equals to base plus IC. So in other words, emitter is always greater than, as I explained here, this plus sign. So emitter is IE is always greater than IC. If IE is always greater than IC, means to say denominator is always greater than IC, then its answer should always less than 1. So typical values of the alpha DC range from 0.99 to 0.95, much closer to 1 but less than 1. Let's take a look at this example. Determine the DC current gain when beta DC and the emitter current gain IE for a transistor where we have to calculate the beta DC and the IE. First of all, let's calculate the beta DC, and when IB is a 5 microampere, that is very less, then you can see that this is in milliampere, which is greater, which means IC is greater, that is in 3.65 milliampere. So beta DC can be calculated as beta DC is equals to IC over IE. Beta DC is equals to, what is IC? 3.65 milliampere divided by 5 microampere. So 3.65 into 10 raised to power minus 3 ampere divided by 5 into 10 raised to power minus 3 into 10 raised to power minus 3. This can be cancelled, and 3.65 divided by 5, the answer is 0.073. When this minus 3 goes towards upside numerator, this become positive 3, and 75, answer is 75. And you know that this is a ratio, so it does not have any symbol. It means this is 75% output is enhanced, and this, you can see that this is a gain. And next, IE, how IE can be calculated? IE formula is very simple, IB plus IC. What is IB here? 5 into 10 raised to power minus 6 plus IC 3.65 into 10 raised to power minus 3. 5 into 10 raised to power minus 3 into 10 raised to power minus 3, or in other words, to simplify this, it means that it is 0.050 into 10 raised to power minus 3 plus 3.65 into 10 raised to power minus 3. I'm just trying to same the both units. The answer is finally 3.7 milliampere. You can just perform these calculations by calculator, but don't forget to conversions. These are the very important. If you have any confusion, mathematics are also available on our platform. At the end, I'm giving you the homework task. That is, the beta DC is if 200 and IB is 50 microampere, you can calculate IC and